Okay, welcome back to this course on stereochemistry. We have so far covered some of the basic concepts of chirality, stereoisomerism, and then the assignment of absolute configuration, relative configuration, and we started the prochiral faces, prochiral centers, and how to designate them. And then finally, we started last time the conformation analysis, but then I realized later on that we should discuss. So far, we have discussed only the chirality involving the carbon centers. We have not discussed any system where the chirality is originating from some other atom other than carbon. So, let us have some concepts about molecules where chirality is exhibited by where the chirality is due to the presence of a non-carbon center. So, let us start with the atom nitrogen, because the important thing is that the atom that we will consider, the non-carbon atom that we will consider should be tetrahedral, should have a tetrahedral geometry, and then the concept of chirality only arises. So, we will pick up atoms like nitrogen, tetra coordinated nitrogen, which is tetrahedral, that we know, and then we also have phosphorus, the next atom in the same group of nitrogen. So, you can go down nitrogen, phosphorus, arsenic, antimony, bismuth, and we can discuss the stereochemistry that is involved in all these in this series, but just for this course we will restrict our description only to the case of nitrogen and phosphorus. So, let us start by showing you the case of nitrogen. Now, if you take nitrogen and trivalent nitrogen, which is tetrahedral, that we know, the geometry is a trigonal shape, but the whole structure is tetrahedral, because structure you have to consider the lone pair also. So, if we consider the lone pair as the fourth ligand, then you have the other three ligands. In ammonia, these three ligands are hydrogens, and this is the lone pair. Now, if these three ligands are not ammonia, but derivatives of ammonia, where the derivatives are such that these groups are different. I have here shown the difference by color difference. So, these three groups are different, and lone pair is obviously another entity, different from the ligands, but that is also considered as a group or a ligand attached to the nitrogen. So, lone pair is also here considered as a group attached to the nitrogen. Now, if it is so there are four groups basically. Now, there are four groups arranged in a tetrahedral fashion, and all four groups are different, and so this nitrogen belongs to the class of a stereogenic center or the so called chiral center in case of carbon. And so, this nitrogen is a chiral center, okay, because all the four ligands are different. Okay. I again repeat, lone pair also, although it is not connected to any group, but here for the sake of simplicity you consider it as a fourth ligand, and so this should be chiral. And now, its mirror image is drawn here. If you put a mirror here, then this will be the mirror image of this molecule, and they are not superimposable, exactly like the carbon system. Okay. However, there is a problem here. If one tries to isolate one of these enantiomers, so they are basically enantiomeric pair. Now, if you want to isolate this enantiomeric pair, it is not possible to do so, because there is a rapid interconversion between this enantiomer to this enantiomer and vice versa. Okay. So, they rapidly interconvert into one another, and this interconversion is what is called the nitrogen inversion phenomena. What is nitrogen inversion phenomena? That means the lone pair, which was earlier pointing towards this direction, that now inverts its position, comes to the left side, and these two groups which were towards the left hand side now goes to the right hand side. Okay. So, that is what is called the inversion in case of nitrogen. The same inversion will come to phosphorus, also happens in phosphorus. In nitrogen, this inversion is has a very low barrier. For any process, you know that there is a barrier involved. Now, in this case, these are enantiomers, so they will have the same energy, but there will be a barrier to this inversion process. Now, this barrier is such in case of nitrogen that it happens at the room temperature. So, if the barrier happens at, if the inversion happens at room temperature, that means one enantiomer is converted to the other enantiomer at room temperature. So, it is not possible, the moment you try to isolate this, then that 50% of this will be converted to 50% of the other enantiomer. So, it is not possible to isolate these enantiomers in case of nitrogen. Okay. Now, that inversion can be described beautifully by this diagram. Suppose you have an inverted umbrella like this, and what happens in spin inversion is that goes into another inverted umbrella which will look like this. Okay. So, if this is the lone pair earlier, so now the lone pair is occupying this side. Okay. So, this is the inversion process. So, due to this inversion process, it is not possible to isolate the enantiomers in case of nitrogen. However, there are ways to, let us inspect this inversion process again through the slides. What happens here, because this inversion cannot happen by just that jumps and go to the right side, that cannot happen. What happens here the nitrogen is started as a sp3 hybridized nitrogen, but during the inversion process at the intermediate stage it becomes sp2, where these three groups R1, R2, R3, here these are described by different colors. Here now I am putting three different groups R1, R2, R3, and this nitrogen was sp3 to start with, the lone pair is at the top. Now, what happens, as it tries to go to the bottom, it has to go through this intermediate, where this is the nitrogen becomes sp2 hybridized, and now this is a pure p orbital. So, this is now brings all the three groups in a planar orientation, that means now the nitrogen has lost the chirality in this configuration. It has lost chirality, but it regains chirality by now again changing the hybridization to sp3, but putting the lone pair in the different direction, just in the opposite direction. So, now the lone pair is occupying an orbital which is the bottom orbital, earlier it was at the top. The most important point is that this inversion process involves an intermediate where the nitrogen is sp2 hybridized and it has lost the chirality. So, actually you will know later on that to go from one enantiomer to another enantiomer, that means which is called inversion, you need to go through a planar molecule and then go to the non-planar molecule to bring back the chirality. While going into the non-planar molecule, you have the option of either going to the starting point or going to a product point. So, that is what happens here. So, the starting point is this non-planar is chiral, then you go to a planar system which is achiral, and then it had the option of going back or going further to go to the opposite enantiomer. Okay. So, this process, as I said, happens at room temperature, okay, because the barrier to the inversion barrier is only 6 kilocalorie per mole for R equal to alkyl, because the inversion barrier depends on the size of, definitely it will depend on the size of these different alkyl groups. Okay. So, the inversion barrier may vary. So, it is around roughly 6 kilocalorie per mole when R is equal to an alkyl group, a small alkyl group, say methyl. Okay. Now, the question is that why the inversion barrier in nitrogen is so low. and which actually is inhibiting us to separate the two enantiomers of nitrogen. So, let us draw that nitrogen compound, the trialkyl nitrogen compound, and we are now come to the very basic question that why is this inversion barrier so low in nitrogen. Just to mention that if you go to the next element in the periodic table along the nitrogen group, you will see phosphorus, and in phosphorus the inversion barrier is quite high, and it is such an amount that allows the phosphorus compounds, the chiral phosphorus trialkyl compounds, isolable at room temperature. Okay. So, now the question is why is that? Why the inversion barrier is phosphorus high and in nitrogen it is low. So, this is the effect of inversion. Okay. So, the lone pair was earlier up and now it is down. Now, one thing is clear, that was shown earlier also, that while going from this to this, the nitrogen has to go through a pyramidal shape, that means the groups have to be pyramidal. And this orbital, the lone pair now assumes a pure p orbital. So, this is p orbital, and the nitrogen you can call that it is assuming a trigonal bipyramid structure. Okay, that includes the lone pair. So, the conversion is basically you have supposedly an sp3 hybrid orbital, and that goes to the earlier it was up, now that goes to the down sp3 orbital via the intermediacy of a p orbital. Okay. Nitrogen is 2p orbital. Okay. Now, what happens in nitrogen, you know that these angles are never maintained at 109 degree 28 minutes. It is slightly less because of this lone pair bond pair repulsions, and they balance at a value where the angles are these angles we are talking about is about 107 to 105 degree. It varies with the nature of the alkyl groups. So, it is slightly less than the expected value of 109.5 degrees. Now, if you look at these different hybridization states sp3, sp2 and sp, what happens here? The bond angle, the correct bond angle, if it is pure sp3 is 109.5, here it is 120 and here it is 180. So, what we see that as the p character increases, the angle goes down. Okay. So, that means in nitrogen, because the angle is less than 109 degree, 109.5 degrees is less than that. So, the percentage of p character in these bonds, in these hybrid orbitals making the bonds, the percentage of p character will be more. Okay. In order to lower this. Now, that and how much will be the p character, excess p character, that depends on the how much deviation is from the actual bond angle. Okay. So, this has got, this is not pure sp3 now. So, it will correspondingly has some extra s character. But if you go to the phosphorus case, the inversion, spin inversion, if you consider in the phosphorus, then what happens? These angles are close to 90 degree, and if it is close to 90 degree, that means these have got much more p character than the bonds which are in the trialkyl nitrogen. Comparing the nitrogen and phosphorus, this has got more p character and this has got much more. This extra p character will be extra s character, sorry, s character. Suppose this is x percent, extra s character, and this is y percent. So, what we can say that y is much greater than x. So, this has got much more s character. Now, the Inversion means that it has to go from this orbital has to go from here to an sp2 orbital. So, the orbital which has got already very high s character, for that orbital to go into the pure p orbital will be much more difficult than an orbital which has got which is close to sp3 hybrid orbital, but the s character is not way beyond sp3, because the angle is only 107 to 105 degree. So, again I repeat the thing that because the s character of the orbital containing the lone pair in trialkyl phosphine is much more than the expected sp3 as compared to the nitrogen. So, this one, for it to be converted to a pure p, if we convert the intermediate, that is the intermediate, conversion of this to pure p will be more difficult, and that is why you have a higher barrier to inversion in phosphorus than in comparison to nitrogen. Now, this is one argument. There are other arguments you can also put forward, and scientists also have done that. Another argument is much easier. The argument is that in the intermediate stage, the angle between the alkyl groups is 120 degree, and in the nitrogen case the earlier angle was about 107 to 105 degree. So, now you have to increase the angle, but the increase is about 15 to 13 degrees to reach to 120. In case of phosphorus, the angle is about 90. This is about 90. Okay. So, now from 90 to goes to 120, that means you have to increase the angle by about 30 degrees. So, you need more energy to do this deformation. Okay. So, you need more. So, you can explain as per the S character, greater S character of the phosphorus lone pair, or you can explain in terms of this angle concept, that the angle was almost 90 earlier and you have to push it to 120 in the intermediate. So, it needs more energy than that in case of nitrogen, where the angle was about 107 to 105 degree, and that is going to 120. So, it is a much less amount of deformation in angle. So, that is why the inversion barrier in nitrogen is very low. A third argument, which is based on quantum mechanical concept, which is little difficult, I can just simplify, I will not go into the details. What it says, that the nitrogen energy barrier in going from one state to the other, one state means one state is this one, the other state is the inverted one. So, in going from this to that, the energy barrier has a much lower width than in case of phosphorus. So, in case of phosphorus, if you do the phosphorus chemistry, so if you do the same thing, the phosphorus energy barrier is, the width is very high. Okay. The width is very high, and there is an effect called tunneling effect in quantum chemistry, that even if there is a barrier, some molecules can go from this side to that side by what is called the tunneling. So, there it is like physically you can think of a tunnel, and this tunnel, the width of the tunnel is much less in case of nitrogen than in case of phosphorus. So, what it makes, the tunneling, due to easy tunneling effect in nitrogen as compared to the phosphorus, because of the greater width of tunnel in case of phosphorus, makes the nitrogen the nitrogen inversion much easier as compared to the phosphorus. Now, this is entirely done by quantum mechanical calculations. Okay. So, these are the three explanations that are given. Possibly this is the correct explanation, but others are for organic chemists. I think the others are also quite okay, because it fits to the general concept of organic chemistry, which is based on hybridization states of the atoms. Okay. Now, inversion becomes slow. How can you now isolate chiral nitrogen compounds? The only way to do it by slowing down the inversion. By slowing down the inversion, that means increasing the inversion barrier. If you increase the inversion barrier, then you can do that. And in case of this three membered ring nitrogen, which are by the way called aziridines, they, in that case nitrogen is very difficult, because it is a three membered ring, and to convert the nitrogen, to invert the lone pair from here to this position is difficult. Actually, this is written in particular form. I can write it here to show it in a better fashion, that so this is the lone pair and this is the, suppose this is methyl. So, the inversion means this is here and the lone pair is there. This is what is the inversion. Okay. Now, this inversion requires the nitrogen to be in the intermediate. As I said, it requires the nitrogen to become from sp3, then it goes to an sp2 nitrogen and then go to the sp3 back, because this is the intermediate and sp2 hybridized nitrogen is the intermediate. So, if that happens, if that is the requirement, then it will be very difficult to do it in a three membered ring, because three membered ring already there is lot of angle, you will learn this, lot of angle strain already is there, but to make it when it is sp2, the angle has to be 120, and which increases the strain in the molecule. So, virtually what you are doing, then you are slowing down this process. So, here the energy barrier is more. Why? Because to have a planar nitrogen here is very difficult in a three membered ring. And so, the inversion barrier, you can conclude from here that as the ring size increases, the inversion barrier decreases. Okay. And ultimately, it will be very fast at room temperature. Suppose you take a 6 membered ring containing nitrogen, then the inversion barrier is very low, and that will almost be similar to the acyclic system, where there are 3 alkyl groups attached to the nitrogen. Okay. And in fact, in this case, the enantiomers can be separated and have been separated. Okay. There are other examples like this, the same, the aziridine. I said this actually works in case of 3 membered ring. It also works in rigid systems, bicyclic systems, where the nitrogen also cannot adapt a planar configuration in the intermediate, like this compound, where the nitrogen is the 2 nitrogens are connected by a bridge, 1 carbon bridge. These are what are called Trojer's base, and the Trojer's base, these 3 bonds, this is one bond, this is the other bond, and this is the third bond, and these 3 bonds, you cannot actually, it will be a tremendous strain that will be incorporated in the system if you want to bring these 3 atoms in the plane. So, Trojer's base, if they are properly substituted, they become chiral molecules. Okay. That is a classical, the first, I think the first nitrogen compounds which are isolated as chiral materials or as chiral compounds. Okay. In case of phosphorus, as I said, phosphorus, the inversion barrier, earlier it was 6 kilocalorie per mole, now the inversion barrier is 32.7 kilocalorie per mole. Okay. And these compounds, so there will be, you can easily separate them, because the room temperature does not allow you that much of energy to invert. The phosphorus inversion case is not possible at room temperature. So, one can isolate these compounds, and see this compound has been isolated and it has got an alpha D. Indeed, they have shown that yes, they are chiral as predicted because what is the fourth ligand that is missing here, that should be the lone pair, okay, and the lone pair here should be at the bottom, okay, and the relationship between these two will be enantiomers. So, one of them have been isolated, one of them means not this one, a different compound, it is an allyl group, a methyl group and a phenyl group and a phosphorus, and the sign is not here. So, possibly it was plus. So, plus the alpha D of this compound is plus 16.8 degree. So, it is indeed, it was proven that the phosphorus compounds are chiral compounds. Okay. Now, you can have when there are 4 different groups attached. Now, unlike this in the lone pair, which can invert from one side to the other or one face to the other face, if you have 4 different groups, then that possibility is gone. Okay. So, then there is no inversion, and you can make nitrogen compounds, phosphorus compounds or sulfur compounds, where there are 4 different groups which are attached, 4 different groups. So, there is no question of inversion. So, you can isolate them, they can exist as a pair of enantiomers and you can separate them like this. These are called quaternary ammonium salts. So, quaternary ammonium salts where all the 4 groups are different. So, you can have, they can exist as enantiomeric pair and it is possible to separate them. So, that is the example of the nitrogen. Phosphorus, if you have this phosphonate where there is one oxygen, one attached to the hydrogen, another is OCH3, another is OCH to CH3. So, these 2 groups are different as well as these 2 groups. So, then basically the phosphorus, this is tetrahedral in geometry and it can also exist as a pair of enantiomers, you can separate them. Okay. So, there is no question of inversion. So, that is an example of phosphorus compound, and of course, phosphorus even trivalent, you can, I have shown that the inversion barrier is low. So, trivalent you can separate also, in the tetravalent obviously will be possible, and in case of sulfur, say sulfone like this, these compounds are called sulfone, where one oxygen is 18 O18, another oxygen is O16. So, they are not the same, they are different, although they are isotopes, but they are different. Okay. So, they can also exist. The sulfur is again is a tetrahedral sulfur, it is not planar, because I told that in planar system you cannot have this type of optical isomerism, this type of stereoisomerism, means this enantiomerism. So, this because the sulfur is tetrahedral and because there are 4 different groups, so it exists as a pair of enantiomers. Okay. So, that ends up the case of non-carbon containing non-carbon the chirality of compounds, where carbon is not the is the key cause for chirality. It is the other atoms like nitrogen, sulfur or phosphorus. Again I repeat, the most important point is that they should be in the tetrahedral configuration. They should have a tetrahedral configuration. Okay. Now, just before we finish this part, let us see these compounds, because they are chiral. So, they should have also optical activity. They should have optical activity and they should also have absolute configuration. What is absolute configuration? The exact arrangement of the groups in the space, and we have different notations. I explained the DL nomenclature system, capital D, capital L, and also the RS nomenclature system. So, how to assign RS to these compounds? Just one example, say in case of aziridine, because I told you that in case of aziridine, the compound exhibits, the compounds can be separated. See, any trivalent nitrogen where all the groups are different, they show optical isomerism, but the problem is you cannot separate, you cannot prove them unless you basically go at very low temperature where the inversion cannot take place, then it is possible to separate them. But to my knowledge, nobody has done that yet. So, the only compounds that are chiral nitrogen compounds are the aziridines and the quaternary ammonium salts. Okay. So, suppose you want to assign the RS nomenclature system in this molecule to the nitrogen, okay, to the nitrogen. So, now in order to make these two groups different, you have to put something here. Okay. Suppose I put a group R1 or a methyl here. Now, I ask that what is the configuration of this of the nitrogen here. What is the configuration of this nitrogen? So, how do you do it? I think I gave you, because these two are, one is below the plane, this is above the plane, this is in the plane and this is in the plane. So, what you do, you stand here in an orthogonal position to the plane, extend your right hand and left hand, and if you do that, so the groups will be spread out. These groups, this will look exactly like your Fisher projection formula, what it should appear like. So, when you look from this side, but standing this way, standing in an orthogonal position. So, your right hand will be towards, your right hand towards will be this will be to your horizontal direction to your hands, and these two, this will go down, that will be towards the bottom, and this will go up. Okay. So, now the priority sequence will be, this will be 1 obviously, because there are 2 carbons attached to this carbon, one is this carbon, another is this carbon. This will be 2 because there are 1 carbon attached, extra carbon attached to this carbon. This will be 3 because only hydrogens are attached, and lone pair is 4. Lone pair is always the least priority group that I told you after hydrogen. So, this is the scenario. So, you stand here, extend your hands. So, on the 2 hands, the 4th group is going to your right hand, the 3rd group is going to your left hand, and on the top number 1 and on the bottom number 2. Now, you do the RS nomenclature. You can bring the 4th group at the bottom if you wish, or at the or here also, any of the vertical position that you can do, or I said that you can just check here, and then whatever you see you can invert that. But let us do a exchange in a group of 3. So, 4 comes here, 2 goes there, 3 goes there, 1 remains as such. So, 4 here, 2 there, 3 here. So, if you do that, now you do the RS. So, it becomes S. So, whatever you see, that is the configuration of the nitrogen. So, the nitrogen is now in the S configuration. Okay. I hope this is clear, that how do you just stand orthogonal with your head on this side and then spread your hands. So, the molecule will look exactly what it should look like before you draw the Fisher projection. Okay. So, that takes part of the configurational assignment of non-carbon systems. Okay. Thank you.